Hello friends, so this is part 4 for the year 2023, and here we are going to solve 11 questions, and all these 11 questions are from the mains. So this will be the last part of the mains. In the next part we are going to solve all the 2023 advanced questions. So first question, it states that as shown in figure, a cuboid lies in a region with electric field 2x square I unit vector minus 4y j unit vector plus k unit vector Newton per coulomb. The magnitude of the charge within the cuboid is n epsilon naught coulombs. The value of n is, if the dimension of cuboid is given as 1:2:3 meter cube. So basic figure is given to us, and it is given basically a cuboid, and we have we have to find out the magnitude of charge within this cuboid, and for that we are going to use, for you can say, Gauss law, that is electric flux through a closed surface. And we are given the equation for the electric field, and it is said that electric field is our 2x square I plus 4ij and plus 6k unit vector. And if we see this equation closely, we can from here see that this first part, that is a 2x square I unit vector, is a representation of the electric field in x direction, and the second one is the representation of our y, and the third one is the representation of our z. Along with this, we can also draw a conclusion that our E of x is dependent upon the square root of this, so not square root but square of x. E of y is dependent upon our y, whereas E of z is a constant. Okay, so this we can just draw a conclusion from the given equation. Therefore, let us first of all find out with respect to the electric field that is in x direction. Okay. So we say that flux through x faces x faces means which is in x direction, so that will be both left and right. So x faces is our both left and right faces, and as per the figure given to us, you can see at left face our value of x is equal to 0. So you can say at x equals 0, which is basically our left face, we can write that our electric field E of x will be equal to, which is 2x square, and we substitute value of x as 0, which gives us that our E of x will be equal to 0. So which means that the flux associated with the left face will be equal to 0. Now we come to the at x is equal to 1. My mistake. 1 second. The phase which I is so we can say at x equal to 1, which will be our, no, I cannot see it left and right. Let me rephrase it. Because the cube will be this is our x equal to 1 and the backward phase will be equal to our x equal to 0. So this is front and back, not left and right, sorry. Okay. Because this is x is 0, x equal to 1 and this is our x is equal to 0. And therefore we can say this will be a front face, and for x is equal to, let me clear everything. So we are going to have at x equal to 1 and x equal to 0. So it is front and back face. Front and back face. And at x equal to 0, we are going to have this as a back face. And at x equal to 1, we are going to have the front face. Therefore, we can write that our E of x will be equal to 2 1 square, which comes as 2, and our area will be equal to, this will be our 3 multiplied by 2, giving us 6 meter square. One second. Yeah. So we can say our flux, this will be our back. Flux front will be equal to, and this will be coming as our E of x multiplied by area, which gives us 2 times 6, coming as 12 Newton meter square per coulomb. Therefore, total flux in x direction, total flux in x direction, we can say that is phi of x will be equal to 12 minus 0, giving us 12. Similarly, we can find out with respect to our y. So we can say flux through y faces, and y faces will be our front and back. So we can say that our So our at y equal to 0, which will be our back face, we can say that E of y is equal to, it is given as minus 4y, which gives us 0. Therefore flux associated with our front, sorry, not front but back, will be equal to 0. And at y is equal to 2, we get E of y is equal to minus 4 multiplied by 2, giving us minus of 8. And here our area will be equal to our 1 multiplied by 3, giving us 3 meter square. Therefore our flux back front will be equal to minus 8 multiplied by 3 is equal to minus of 24. So net flux in y direction, total y direction flux will be our phi of y is equal to minus 24 minus 0, giving us minus of 24. Similarly, we find out our finally flux through z phase. Z phase is, which is our top and bottom. Top and bottom. And here our E of z is equal to 6. So it means the flux E of z at top as well as bottom will be same. So we can say our flux top will be equal to flux bottom, which will be 6 multiplied by the area. Therefore the net flux that is above phi of z will be equal to our 6a minus 6a is equal to 0. Therefore we can say net flux through the cuboid. Net flux through the cuboid, let us call this as phi net, will be equal to phi x plus phi y plus phi z. We substitute the value. Phi x is our plus 12, phi y is our minus 24, and phi z is 0, which gives us minus 12 Newton meter square per coulomb. And okay, we have to find out here charge. Sorry, my mistake. So flux we found out. So charge we can just easily say that our charge, let us suppose it is given as Q enclosed. Therefore we can write that our using Gauss law, we can say that our flux is equal to, we have our charge enclosed divided by epsilon naught. Okay. Therefore, we can say that our net flux, from here we can just write it as, the equation it is given as the magnitude of charge enclosed is n epsilon naught. Okay. And we are given that charge enclosed will be equal to our flux and epsilon naught, but we are given this is equal to n times epsilon naught, and we substitute, we get this as minus of 12 epsilon naught is equal to n times epsilon naught, giving us value of n is equal to minus of 12. This is our minus of 12. Next question. We are given a cuboid of dimension 2L by 2L by L. A charge Q is placed at the center of surface S with a surface area 4L square. The flux through the opposite side is. So basic figure is given to us. We are given that we have a charge Q which is placed on this top face, and we have to find out the flux which will be through this opposite face. And for that we are going to draw a symmetric cuboid, so that, because we are going to use Gauss law, and Gauss law always talks about the charge enclosed. So we are going to draw a cuboid which will be symmetric to the given cuboid. And in this condition we can just so this is our cuboid, and because of this cuboid the total length now becomes 2L, and the rest of the dimension will be same. So this will be still 2L, and the width will be also over 2L. So because of the symmetricity, we can say that by Gauss law our flux total will be equal to our charge enclosed divided by epsilon naught. Charge enclosed is our Q. Therefore we can say our flux associated with this entire setup will be equal to our Q upon epsilon naught. And here from figure we can see that by this entire is now in the shape of a cube, because every dimension is 2L by 2L by 2L. So we can say that the Gauss surface is symmetric. Symmetric means 2L by 2L by 2L, so which is basically we can say a cube. Therefore we can draw a conclusion that all the faces are going to have a equivalent share of the flux. Therefore we can say all faces are equivalent in terms of share of total flux. Therefore, we need to find out the bottom phase. So we can say flux through the bottom phase will be our 1/6 of Q upon epsilon naught. So option number 2 is correct. Option 2 is correct. Next question. States that a point charge Q1, which is 4 times Q naught, is placed at origin. Another point charge Q2, which is minus of Q naught, is placed at x is equal to 12 centimeter. Charge of proton is Q naught. The proton is placed on x-axis so that electrostatic force on the proton is 0. In this situation, the position of the proton from the origin is dash centimeters. So here we are given that we are having, suppose this is our origin, and at here we are placed a charge that is Q1 whose magnitude is 4 times Q naught, and at a distance x we have placed a point charge that is our Q2, which is our minus of Q naught, and this x is given as 12 centimeters. And it is said that this proton is placed along x-axis. Okay, so this is our x-axis, positive as well as negative, and this is our origin. So this is our origin, and we require that the electrostatic force on this proton is equal to 0. So proton is basically very positively charged. Therefore, we can say that the force due to our Q1 will be repulsive and force due to Q2 will be attractive. Okay. Therefore, we can say that proton is repelled by Q1, which is our 4 Q naught, and this Q naught, this is placed at, sorry, not Q naught, but Q1 is placed at x equal to 0. Therefore, okay, this is the first part, and in the second part the proton will be attracted by Q2. The proton is attracted by Q2, which is our minus Q naught, and it is placed at x is equal to 12 centimeters. And for the sake of convenience, we require, okay, and we have to also understand that the charge of Q1 is close to 4 times the charge of our Q2. So obviously its force will be, repulsion force will be on the higher side as compared to the attractive force by Q2. So let us assume that we say consider the proton is at position which is x greater than 12 centimeter. Okay. So it means proton is somewhere here, okay, because this is x greater than 12 centimeter. So because of this, the repulsive force, that is our, so from here we can say that our repulsive force will be towards the right side. Repulsive force will be towards right side and attractive force will be towards left. Attractive force will be towards left side. And there should be, net result should be 0. Therefore we can say force repulsion should be equal to force of attraction. And so here let us consider that the distance of proton to Q1 is our y and Q2, one second. One second. This, if I assume here, so it will be in this direction and it will be in this direction. I think this is correct one. And if I assume somewhere here, then because of Q1, so let us assume that, this is our y, and I think there is some problem from my side. One second. Yeah, got it now. That was my mistake. But this will be repelling in this direction and this will be also attracting this direction. Yeah, now I got it. So let us assume that we are having ny, and so we have this distance is, let us suppose, y. So therefore the total distance will be our y plus 12. That's correct. So we have a repulsion force that will be our K, and we get this as 4 Q naught multiplied by Q naught. So this comes as 4 Q naught square divided by y plus 12 whole square is equal to, and we get this as K Q naught square divided by y square. Here K Q naught square K cancels out. So we get from here 4y square is equal to y square plus 12 and whole square. And this gives us that our y plus 12 is equal to our 2y, which giving us 2y minus y is equal to 12, giving us y is equal to 12. One second, why 12? I made some blunder. Okay, so we have to find out this from origin. So this is correct, not a blunder. Therefore we can say the distance from the origin will be equal to x plus 12, which will be coming as 12 plus 12 and giving us 24 centimeters. This comes as 24. Next question. It says that a point charge 2 into 10 to the power minus 2 coulomb is moved from P to S in a uniform electric field of 30 Newton per coulomb directed along positive x-axis. If the coordinates of P and S are 1,20 and 0,0 meter respectively, the work done by the electric field will be. So we know that the work done is equal to our force and displacement, and force is charge multiplied by the electric field. And here we are given that electric field is along x-axis, so we can just draw, because z component is 0, so we can just draw it with respect to x and y. So first, the coordinate of P and S. So where S is at origin, so this is S 0 0 0, and we have x1 and y2, and we can just say, let us suppose this is our point P. We are having this coordinate as x1 y2, and this is origin 0 comma 0. So we can say if this r is the position vector, and we need to find out the work done by the electric, okay, and electric field is directed along positive x-axis. So electric field is directed along our positive x-axis. So we can say that our work done by electric field, let us suppose that is W is equal to our charge, electric field, and displacement D, where this is representation of our r vector, position vector. And we can easily find out our D. D will be equal to our, let us suppose this S is having a position vector of RS, and this RP is represented as our RP. P is represented as RP. Therefore, we can say this will be RS minus RP, and this will be coming as 0 minus 1 I unit vector plus 0 minus 2 J unit vector plus 0 minus 0 K unit vector. Therefore, our D, which we have called here as R, will be equal to minus I and minus 2J. And we need to find out the dot product of the electric field and this displacement vector. Therefore, we can say that E dot D, electric field is given in x direction, so this comes as our 30I dot minus I minus 2J. We can write this will be equal to our 30 minus 1 plus 0 is equal to minus of 30. Now we can easily find out our work done. So we can say our W will be equal to charge multiplied by minus of 30, and charge is our 2 into 10 to the power minus 2. 2 into 10 to the power minus 2 multiplied by minus of 30. This gives us a minus 60 into 10 to the power minus 2, and we can call this as 600 millijoules. So work done will be minus 600 millijoules. So option number 3 is correct. 3 is correct. Next question. We are given that for a spherical ball, electrostatic potential inside the ball varies with R as V is equal to 2A R square plus B. Here A and B are constant and R is the distance from the center. The volume charge density inside the ball is minus lambda A times epsilon. The value of lambda is, where epsilon is the permittivity of the medium. And we know that our first of all we are going to find out our electric field, and from electric field we can use Gauss law to find out the charge. Okay, and that will be, from there we can easily find out our volume charge density. And we already know the relationship between electric field and our potential, we can say our electric field from potential. So electric field with respect to distance r will be equal to derivative of our potential, and v is given to us, equation is given, so we can say this is derivative with respect to r. This comes as 2a r square plus b, and this comes as 4a r, and our this I forgot to here minus 4a r. Now we can use Gauss law. And Gauss law gives us that for an enclosed surface, the E into dA will be equal to our charge enclosed divided by epsilon. Here we are going to take epsilon because it is a different medium, not epsilon naught. And we can write this as our E, and area will be over 4 pi r square, and we have our charge enclosed divided by epsilon naught. And our charge enclosed, we can say our charge density, which is nothing but volume charge density, so charge density multiplied by the volume, 4 pi r cube. So we also know value of our electric field, so we substitute this, becomes minus 4a r multiplied by 4 pi r square is equal to our charge density multiplied by 4 pi r cube. And we can just pi and pi, this r also cancels out, 4 goes with 4, therefore we get our rho will be equal to, this comes as 12, I forgot one thing here, what is that, charge enclosed divided by epsilon. So we get this as, will be coming as minus 12 times epsilon, and we are left with a. Therefore we are given that the charge density is minus lambda a epsilon. So we got our rho is equal to minus 12 a epsilon, which is given as lambda and a epsilon. So from here the value of lambda will be equal to 12. 12 is the value of the lambda. Next question. It states that a parallel plate capacitor has a plate area of 40 centimeter square. The plate separation 2 millimeter. The space between the plates is filled with a dielectric medium of thickness 1 millimeter. The dielectric constant is 5. The capacitance of the system is. So here we are having a capacitor, and the distance between the plates is given to us as 2 millimeter, and it is filled with a dielectric whose thickness is 1 millimeter. So it will be covering almost half part. So this is a dielectric which is of thickness of 1 millimeter. Therefore the air gap which will be remaining is also going to have a thickness of 1 millimeter. Area of the plates will be same, it is not going to change. dielectric constant of this dielectric is given to as 5. Therefore, we can clearly see that we are having two capacitors. One is which is air as dielectric, and other one in which we have a dielectric. Let us suppose that is C2, capacitance is C2, which is having a dielectric of 5, and these two will be in series. Therefore, we can say that total capacitance if we call that C, which will be a series combination. Series combination. And we can write this as 1 upon C is equal to 1 upon C1 plus 1 upon C2. And let us call it as the thickness of, we can substitute the value later on. Let us generalize. Thickness of this dielectric is over x, and this will be over d minus x. And total is over d, which is given as 2. So therefore our C1 will be equal to our d minus x and divided by our epsilon a plus x divided by k epsilon times a. Now we can just substitute the values. D minus x was over 1, and we have here epsilon a, and this is our 1 millimeter, so this comes as 1 into 10 to the power minus 3 minus this will be also same 1 into 10 to the power minus 3 divided by 5 epsilon times a, and we can just take the factor as common, which gives us, sorry, this is not minus but plus, and this comes as 1 into 10 to the power minus 3 divided by epsilon a, and we are having this 1 plus 1 by 5, and this comes as 6 by 5. So this will be 6 by 5 multiplied by 10 to the power minus 3, and epsilon area is already given to us, and area is our 40 centimeter square. So this comes as 40 into 10 to the power minus 4, and we can just cancel it, and this will be coming as 1 upon C. Therefore we can say that our C is equal to, this comes as 6 into 10 to the power minus 3, and in the numerator it will be 5 into epsilon multiplied by 40 multiplied by 10 to the power minus 4. So this gives us that the equivalent capacitance of the system will be equal to 10 by 3 epsilon naught. So this will be 10 by 3 epsilon naught farads. So option number 2 is correct. Option 2 is correct. Next question. We are given a point charge 10 to the power minus 10 microcoulomb is placed at origin. At what location on the x-axis should a point charge of 40 microcoulomb be placed so that net electric field is 0 at x equal to 2 centimeter on the x-axis? So we are given 2 point charges and they are placed to be at on the x-axis. So let us suppose this is our x-axis. First point charge, let us suppose we call this as q1. It is our 10 microcoulomb, and another point charge, suppose we are placing it randomly, that is our q2, which is our 40 microcoulomb. And it says that net electric field is 0 at x equal to 2 centimeter. So let's suppose this is the point, that is our x is equal to 2 centimeter. And we say that this q2 is placed at a distance of d from the origin. Therefore, the distance where we want here that our electric field should be equal to 0. So therefore, this distance will be coming as d minus 2 centimeters. So we can find out the expression for the electric field. So we can say electric field due to q1 at, let us call this as A, B and C. So you can see electric field due to charge at A due to charge at A at point B, at point B. Let us call this electric field as our E1. So E1 will be equal to our K Q1 and divide by 0.02 whole square. And its direction will be towards right. Towards the right side. Okay, so E1. So this will be our E1 toward the right side. Similarly, we can say that our due to Q2 due to charge at C at point B, we can write the equation that our E2 will be equal to K Q2 divided by D minus 0.02 whole square. And okay, so here the direction of this electric field, that is our E2, will be dependent upon the position of Q2. So you can write the direction of E2 depends on position of Q2. So which means that if our D is greater than 0.02, then Q2 is to the right. then Q2 is to the right side of x is equal to 0.02, and we are given that Q2 is positive, so we can say since Q2 is positive, the field at x is equal to 0.02 due to Q2 points away from Q2, points away from Q2, which we see means towards the left. Towards the left. And secondly, if our D is less than 0.2, then Q2 is to the left of 0.02, and we can say that the electric field, at 0.02 due to Q2 points away from Q2, or we can say towards right. And please remember that everything is being discussed with respect to the point which is 0.02. Okay, here also and here also, and which basically means everything is being discussed with respect to the electric field, which should be equal to 0. Now let us find out the position of D. Position of D. So net electric field at B is equal to 0. Net field at B is equal to 0. Therefore, we can write that E1 will be equal to E2. We simply substitute the values. We get this as K Q1 upon 0.02 whole square is equal to K Q2 upon D minus 0.02 and whole square. K and K goes away, and this Q1 and Q2 is given to us 10 and 40 microcoulomb. So we can write this as D minus 0.02 whole square will be equal to, we can write this as Q2 upon Q1 multiplied by 0.02 whole square, which will be 0.02 whole square multiplied by 40 into 10 to the power minus 6 divided by 10 into 10 to the power minus 6. Minus 6 minus 6, 10 and 10, and we are left with this as d minus 0.02 whole square will be equal to, this comes as 4 into 0.02 whole square, and we can just remove the squares. We get this as d minus 0.02 is equal to plus minus 2 multiplied by 0.02, which comes as plus minus 0.04. But we know that our value of d is greater than 0.02. Okay. Therefore, we can say our d will be equal to 0.02 plus 0.04, which comes as 0.06 meters, or we can call this as d will be equal to 6 centimeters. Because this condition is true for this part, because we want electric field should be towards the left, because the electric field due to Q1 is towards the right, so the Q2 electric field should be towards our left. And this is true only when our d is greater than 0.02, because it has to be our left. Means with respect to point, this will be our E2, this is our point B. So we get our, this will be our 6 centimeters. So option 2 is correct. Two is correct. Next question. We are given that a capacitor of capacitance 5 microfarad, when its parallel plates are separated by area medium of thickness d, a slab of material of dielectric constant 1.5 having area equal to that of plates but thickness d by 2 is inserted between the plates. The capacitance of the capacitor in the presence of the slab will be. So we are given that we have a capacitor and let us suppose its capacitance is given as C, which is our 5 microfarad, and its thickness is given as D, and area let's suppose our A. In the second case, a slab is introduced between the plates whose thickness is D by 2. So this is slab, thickness is our D by 2, and this distance obviously will be also equal to D by 2, and the dielectric constant of the slab is given as 1.5. So K is given to as 1.5. Area is our area of the plates is same. So let us call this as C naught. So C naught is given to 5 microfarad and plate separation is D. And let us suppose this new capacitance of the entire system is given as C. And here from C we can clearly say that D by 2 is a capacitor which is having as air as medium, and D by 2 is a capacitor which is having a dielectric which is 1.5. Therefore we can say that our equivalent capacitance with dielectric, let us call this as C1 and let us call this as C2. You can say 1 upon C is equal to 1 upon C1 plus 1 upon C2. And our C1 is of air, so this comes as epsilon naught area, and this is our d by 2, plus this comes as K epsilon naught area, and this is also a d by 2. Now we can just solve it. We get this as, we can take d by 2 as common, so this comes as d by 2 epsilon naught a, value of K we know, this comes as 1 upon 1.5, and 1.5 is our 3 by 2, so this will be coming as 2 by 3, 2 by 3 will be equal to 5, and we get this as d upon 2 epsilon naught a multiplied by 5 by 3. And therefore we can say that our C will be equal to, this comes as our 6 upon 5, and we have here epsilon naught a divided by d, and this is nothing but our C naught, which is given to 5 microfarad. So we substitute it, we get this as our C is equal to 6 upon 5 multiplied by 5, 5 and 5 goes away, and we get this as C is equal to 6 microfarad. So we get the answer as 6 microfarad. Next question. It states that if two charges Q1 and Q2 are separated by a distance d and placed in a medium of dielectric constant K, what will be the equivalent distance between the charges in air for the same electrostatic force? So we want the electrostatic force will be same, should be same, and first they are placed in the medium. We can say electrostatic force in a medium. Force in a medium will be equal to 1 by K multiplied by 1 upon 4 pi epsilon naught. Charges are our Q1, Q2, and distance between them is our d, that is our d square. And let us call this as our F medium. And force in the air that is suppose that is called FA will be equal to 1 upon 4 pi epsilon naught Q1 Q2 upon d square. Okay, we have to find the equivalent distance. Let us suppose this is d equivalent, because forces has to be remain same. So from the given question, it says that we should be having the same electrostatic force. Therefore we can write that our force in the medium is equal to force in the air. We substitute the value. Force in the medium is 1 upon K, 1 upon 4 pi epsilon naught Q1 Q2 d square is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon d square equivalent. Here this 1 upon 4 pi epsilon naught Q1 Q2 cancels out. Therefore we get that our d equivalent square will be equal to K times d square, which gives us that our d equivalent will be equal to d square root of K, and this comes at d square root of K. Option 3 is correct. 3 is correct. Next question. It states that the electric potential at the center of two concentric half rings of radii r1 and r2 having same linear charge density lambda is. So we are given that concentric half rings, same linear charge density. So let us draw. So this is suppose first half ring, and this is our second concentric half ring, and this is our center. Let us suppose the internal radius is of r1 and external radius is of r2, and they having the same charge density that is given as lambda, uniform density. And we know that the electric potential due to a point charge q, and based on this we can find out the because of the half ring also. So let's first of all find out the charge on each half ring, because we are given as a charge density, and in the formula we require the charge. So we start with charge on each half ring. Charge on each half ring, and so we know if radius is r, then we can say the length of half ring of radius r is pi times r. Therefore, you can say charge on half ring, let us suppose that is given as q, which will equal to lambda multiplied by pi r, that is our length, and we can just divide into two parts, q1 and q2. Therefore we can say our q1 will be equal to lambda pi r1 and q2 will be equal to lambda pi r2. And now we can easily find out the potential due to half ring. Potential due to potential at the center. Potential due to half ring at center. So the first one, let us call this as V1, will be equal to 1 upon 4 pi epsilon naught Q1 upon R1. Substitute value of Q1, we get this as 1 upon 4 pi epsilon naught, and Q1 was our lambda pi R1 divided by R1. And here this R1 pi and pi cancels out. This gives us lambda upon 4 epsilon naught. Similarly, we can write for second half ring, that is V2 will be equal to 4 pi epsilon naught Q2 upon R2, with substitute value of R2, sorry, not about Q2, we get this 1 upon 4 pi epsilon naught, and we have to say lambda pi R2 divided by R2, and this pi R2 cancel. This gives us lambda upon 4 epsilon naught. So total potential at the center. Total potential at the center. Let us call this as V, which will be algebraic sum of V1 plus V2, giving us lambda upon 4 epsilon naught plus lambda upon 4 epsilon naught is equal to lambda upon 2 epsilon naught. So we have option number 1 is correct. One is correct. Next question. States that a parallel plate capacitor with air between the plates has a capacitance of 15 picofarad. The separation between the plates becomes twice and the space between them is filled with a medium of dielectric constant 3.5. Then the capacitance becomes x by 4 picofarad. The value of x is. So we are given that we are having a capacitor and its capacitance, let us suppose we have C1, or we can say C. It is given as 15 picofarad. In the second case, and let us suppose the separation between the plates is D and the area of plate is our A. In the second case, the separation between the plates is increased, that is now double, so this becomes 2D, and it is filled, space is filled between them with a medium of dielectric. Okay, now the space is filled with a dielectric whose dielectric constant is K, given as 3.5. Area is our same. In this case, let us suppose the capacitance is given as C1, which is as x by 4. So let us call C1 and this let us call this C2. So from here we can say our C1 will be equal to epsilon naught A upon D, and C2 we can say this becomes our epsilon naught A, distance becomes double, and we have a dielectric constant of K. K is given to us 3.5 divided by 2, and this becomes epsilon naught A upon D. And this epsilon naught A upon D is nothing but our C1. Therefore, we can write that our C2 will be equal to 3.5 divided by 2 multiplied by C1. Value of C1 is given as 15. So we can write this value of 3.5 divided by 2 multiplied by 15. And this is given to us x by 4. We need to find out value of x. So we just multiply it, we get our x is equal to 4 multiplied by 3.5 divided by 2 and multiplied by 15. And here 4 goes by 2 and this comes as 30. 30 multiplied by 35, which will be coming as 30 multiplied by 3. And 35 multiplied by 3. 35 multiplied by 3 will be our 105. So C becomes, value of x comes as 105. So this completes the part 4 of the year 2025. And this part 4 we solved 11 questions, and all these 11 questions from mains. So in part 1, 2, 3 and 4 we solved only the main questions. In part 5 we are going to cover the advanced questions because main questions are complete from the year 2025. So this completes the part 4, that is 11 questions from the year 2023, not 25, 23. This completes all the questions. Thank you.